So in this presentation, we are going through the different file system and solutions we have to store data in the clusters, and actually how we access them and how we use them when we submit jobs to the cluster. You already went through the Slurm presentation by Damian, in which you learn how do you ask for resources and you submit jobs to run on the clusters. And there he discussed mainly how you ask for the amount of CPUs, the amount of RAM memory that you will need for your job. But in this one, after a brief presentation of how it's based each of the different storage on the CECI cluster, we will discuss how we use them from jobs. But before going into the details, I start with a big warning message. You must keep in mind that none of all the storage solutions that we have in the cluster is backed up. We have in place, of course, different mechanism to reduce the impact of data loss. So different level of RAIDs, different level of data mirroring among different servers. But we can never rule out a big sequence of hardware failure that has at the end the impact of producing data loss. Unfortunately, we had this 2 or 3 times in the past. So you must remember that. So you will copy your data for running your jobs. You will produce output. You will post-process that, and the very important data that you must keep. You must think about copying that over to some other long-term solution, the very critical output that you produce. Here there's a link where it's mentioned some of the CECI universities provide solutions for long-term storage. In principle, it's Namur and the UCL providing solutions right now. The ULB will have soon. But please keep in mind this for all the data that you will produce with your calculations. And just, yeah, in order to properly follow what we are going to discuss in this presentation, you must be already familiar with this previous presentation that you had. So the introduction to HPC at the very beginning given by Fred, where he discussed how is the structure of an HPC cluster. Then, but you must be already familiar with working from the Linux command line, environment variables. That's what we are going to use for pointing to the different storage solutions that we have. We will use also environment variables in scripts that we will submit with Slurm. Well, if you are already not super familiar with that, you might feel a bit lost, but then, yeah, now we will be able to go through it again later on. So just to provide some context, some numbers on the things that we are going to discuss. Now, if we think about a single workstation, a single computer, so a single desktop or a single laptop computer, nowadays the most performant units we have on these devices for long-term storage are NVMe SSDs. So in the consumer range, the best values that we can get for I/O for sequential read and write, it's about on the order of the 2 GB per second. This is, yeah, in the case that we do a sequential write of a big file. But then if we are going to deal with a lot of many small files that we are going to random read and write, then this bandwidth for read-write, it will go to 400, 500 megabytes per second. So if here with the laptop that I have here and I'm using for the presentation, I have this Intel NVMe SSD. if I do a very basic test with a DD doing a sequential write of a big 2 GB files, well, we can get the value, this kind of, I can get for that sequential write about 2.5 GB per second. But so here, this is in the case in which I'm using, I'm running only this task using the storage. And yeah, here so these are very performant units for I/O, as the CPU is accessing this storage solution directly via the PCI Express lens, where the NVMe is connected. So this is to have an idea of what we get in our workstation and what the different things that will happen in a more complex solution as we have in the HPC clusters. So as I said, in the very first presentation where Frederic presented, gave an introduction to HPC, he mentioned that an HPC cluster is a group of many different servers which are linked together. They are interconnected together via a given network solution in such a way that we can see all these machines as a big single computer. But we must keep in mind that it's inevitable that in order to have this big computer power added up altogether by different servers, we are going through the network, and then this big machine is going to access most of the different storage solutions that we have present on them via the network also. We will have also the equivalent of an internal NVMe on the laptop also, but most of the different storage solutions will be accessed via the network. So we can see that here, well, in principle, yeah, we are order of magnitudes different in bandwidth and latency than we will have with accessing a storage unit via the PCI Express lane in a given workstation. But we will see that we can have much bigger storage targets to use. So this slide comes from also from Frederic presentation, where he presenting schematics of how it's built, an HPC cluster, how it's composed. So we have a stack of different, what we call the compute nodes. So each of them is a server or a server which has a CPU, its local storage, and its RAM memory. So we have a big stack of those that they are interconnected via a network, and then we have other servers which are dedicated to work as storage. So they have a big bunch of disks that are going to be accessed by the compute nodes via the interconnect also. And then we have the login nodes, which those are the machines that when you do SSH, Dimitri 3, 5, 2, you land in a login node. So you are working physically from a terminal that is based on this login node. And the login node also, naturally, to see the compute nodes and the storage is plugged on the same interconnect. And so in the previous presentation by Damian, he among the different things that he talked, he mentioned about different kind of file system based on the network. So we have something like he mentioned, like the NFS file system, in which we have a big bunch of clients. So all these can be the compute nodes and the login node. They are clients of this storage solution. And then basically, this storage solution, it's some solution with a lot of disks, and they have a single uplink in the interconnect. which makes it visible from all the clients. So, but there might be 2 or more physical cables with the uplink, but it's just a single uplink from a single storage solution, which is given access to all the different clients. And this is, as he mentioned, this is a typical setup for the home directories. So when you log in on the login node and you see your home directory, and go back to the previous slide, your home, so you log in and you are physically using the resources of this machine, but your files that you see when you log in, they are coming actually exported from via the network from another physical machine, another storage server, which is providing access to that data via an NFS service. And then we have also as storage visible via the network. We have another big group of different solutions which are called parallel or distributed file systems. And in this case, instead of having a single big a single machine with a lot of disks exporting the storage via a single uplink, here we have a set of different servers, each of them with their big bunch of local disks, and they are all, each of them is connected to the network of my whole solution. But we see, so all the clients are able to see the storage provided by this parallel file system, but they are seen as a single entity. You see a single namespace. So your data is actually scattered on all these different physical servers, but you see all of them as a single namespace. So by doing this, you can increase the bandwidth as you have more network uplinks to your global storage solution. You can increase the bandwidth for all the clients to access that kind of storage. And so we will see that we have this kind of solution on some of the CECI clusters, not all of them. And yeah. And then we will discuss how do we use on the jobs and for which kind of jobs those are more appropriate. So as I said already, when you, so this is another schematics similar to the one Fred presented. So in a schematic of an Hpc cluster, so we have all our compute nodes, some logging nodes, which are all interconnected together. And then here I'm representing a single storage server, the NFS, an NFS kind of storage solution that it's so it's exporting via the network a given file system, which is visible by all the clients, so the logging nodes and the compute nodes. And this is how, yeah, well, this is the kind of solution for all the home directories in all the CECI clusters. So as I said, when you log in, your data is not on the physically on the machine or local disk of the machine where you log in, but you are seeing it via the network on a different, coming from a dedicated storage. And then, so we have, so the main point of having the different layers of storage solution that we are going to see is that here, as you can imagine, in the Metro 3, we have about 80 compute nodes, each of them with 24 cores. So you will have a big amount of, in total, you have about 2,000 CPU cores distributed providing all together all the compute nodes. So you imagine you have a lot of different jobs when the cluster is running on top load, which is what's happening most of the time. You're having 2,000 CPU cores processing it, so doing computations, reading, and at some point the computations. So most of that will happen after your job started. It happens between the CPU and the RAM memory of the compute node, but at some point you will read and write. So imagine that, yeah, if you have 2,000 cores that are able potentially to be writing data at the same time. If you would do that all together to via a single network uplink to this kind of NFS solution, it will be saturated. So for that reason, it's in the cluster are provided different dedicated storage solutions with different performance and different use cases. So as I said, the compute nodes, each of them is a machine with its motherboard. It's usually in the CECI they have 2 sockets or 2 CPUs, RAM memory, and they do have local disks connected to the motherboard. So you can imagine it as a big workstation, each of them, and they have local disks. And inside these local disks, we predefine some environment variable that you can access from your jobs. We'll see later. With that, we tag we define this environment variable with the value local scratch. So you will from a bash script, you will access it with the $local scratch or from the terminal. The thing is that this will point to a partition which is inside of the compute nodes. So when you log in, or when you log in to a cluster and you're on the login node, usually it's not defined this local scratch variable, because it only makes sense to access it from a job that is running in a compute node, because it's really a physical partition inside the compute node. And the thing is that, well, here we can get that, as I showed at the beginning, with an example of a sequential write on the SSD of my notebook. Here we can have kind of the performance that we have when accessing a local disk in a workstation. The thing that we will be limited to the typical amount of terabytes that they can have in a single computer, so amount up to 10 terabytes at max. But yeah, we can improve the performance setting the different hard disk or SSDs in a RAID 0 setup. But in principle, the main thing that it will be limited to the amount of storage that I can connect in a single machine. But this is the ideal place. So if you're going to run serial jobs, that they are going to run in a serial jobs, they would fit in the space available that we have as local scratch. The idea is that you use this. So for serial or parallel jobs that will fit, that will use the amount of cores that they will fit in a single node. If the amount of data or I/O that you're going to do fits on the space provided in the local disk, the idea is that you do read and write on this local scratch space. So that way, you are writing, doing all your I/O there, and you are not unnecessarily going via the network to your home. So you do that all during your job runtime, or the I/O on the disk, and at the end you recover and you do a CP and you copy your data to $home, which is some folder, or yeah, we'll see with another variable. But then some of the clusters, they have as I mentioned before, they have another kind of network file system which provides more performance than the one that we have set up for the home. And this space, we predefine it in the CECI clusters with the variable global scratch. So you will access, will point to that path in a script or from the shell with the $global scratch variable. And as the name says, well, this is global. It will be connected to the interconnect of the Hpc cluster, and it will be accessible from all compute nodes and the login nodes. And yeah, well, in the case, we will see details on the different clusters, how this is implemented. And in some cases, it's really a distributed parallel file system, as I mentioned before. But in some others, it's something similar to the home and NFS solution. And the thing is that, yeah, if you are going to submit big MBI jobs, so jobs that can be distributed among different nodes, then you have no option for those jobs but to write in global scratch, because it's a file system that is visible and accessible from all the compute nodes. And so, well, I already mentioned as I was talking that in all the clusters, you will, so $home is predefined by default in any Linux environment. That variable points to, gives you the path of your home directory on each of the clusters. And then you will have local scratch, which only have has a meaning inside a job, and global scratch, which is accessible from any of the nodes. I can show maybe if I here I'm on NIC 5, so I do SSH NIC 5, I land on NIC 5, and we could do echo $home that will give the full path of which is your home, which is where we land. And also echo global scratch will give the full path of the global scratch. And as I said, yeah, well, local scratch only has a meaning inside a job. So by using these variables in scripts or from the shell, you can access these storage locations. And so in just to go into details for Elementary 3 and NIC 5, the one I just showed, I just printed the path in the terminal. They have so for the home coming from an NFS server, you have 100 gigabytes of quota, so it's the maximum amount of data that you can store in your home area. Then we have on the compute nodes, they have their local disks with a given partition to be used that you can point with the $scratch variable, $local scratch variable. And in both cases, it's a partition on a single SSD on the machine, and you can, and it's up to 200 gigabytes on Elementary 3 and up to 370 gigabytes on NIC 5. So in your script that you submit to the queue and it will run in the compute node, if you do a CP or you have some way to dictate to your code to provide the path to where to do to write the output. Well, you provide the $scratch local scratch variable, and you will be writing in this local disk. And you must remember that, yeah, when in these cases, when the job is done, this folder is removed. So before, in your sequence of commands, in your jobs admitted to the queue, you must remember at the end to do a CP to copy back from inside local scratch, to copy back the data that you want to your home, or you could copy also to global scratch in Britain. And global scratch in this cluster is a solution based on a parallel file system called BGFS, among the different solutions that are available. So this is an open source solution of a parallel file system. And as I mentioned, and Damian mentioned before, today it's a file system which is distributed among. It's allowed me to see as a single namespace a stack of different storage servers, each one of them with a big bunch of disks. So each of these servers is connected to the network interconnect of the Hpc cluster. But we see all of them. So each of you have a folder defined on this storage solution. See that the global scratch has my login name at the end. So each user has its own folder pre-created here. And I see it transparently from any login node or compute node. But the data is really scattered and distributed, so that's the parallel file system takes care of storing the data and handling how it is really accessed. But you just naturally see it as a single namespace. You just naturally see it as you see any other path coming even from a local disk. So in the case of Lemaitre 3, this solution is now providing a net full space of 415 terabytes. And in the case of NIC 5, this whole area, it's providing a net size of 520 terabytes. So here you can see that the main thing that you can get, it's not only more performance, but also you can, depending on the amount of servers that you stack and you put in the solution, you can have much bigger amounts of single storage space that you could have on a single workstation. So that allows you to, if you have a parallel job which is able to exploit that to profit of that, you could tackle bigger problems that you won't have in a single workstation. And so for this writing here, in the case of Lemaitre 3, there are no quotas enforced. So you can go right in there as much as you need. But please, always you must keep in mind, you must remember to clean up. So this is shared among all the CECI users. We have about 300, between 300 and 400 active users using the clusters. So always remember to clean up. The idea is that you can, as I said, you can profit of this to do calculations that wouldn't fit on a no matter how big a workstation. But please remember to, when when you're done and you produce the useful output, you did all your post-processing, remember to clean up. In NIC 5, it's enforced by default a 5 terabyte quota. But in principle, if you have a specific computation that you know that you are going to need a bit more, you can talk with the admin of NIC 5, and he will allow you to go for a limited amount of time to go higher of 5 terabyte. And these spaces are during yearly maintenances, they are fully, they have the scratch part on their name. So it's important that you remember that scratch is at any, in principle, at any time, they some kind of sometimes emergency maintenance, they might be pushed or deleted, but in any case, there are programmed planned maintenances in which they are fully deleted. So you will use these places, well, local scratch for these clusters, it will be available. So you will have access to the 200 or 700 during your job runtime, but when your job ended, the data of that temporary folder is removed. But for global scratch, they will be also, they will be deleted in yearly maintenance. It will be when it's a planned intervention, it will be announced on the mailing list in advance. But just remember, as a good habit to have, to always remember to clean up and to move your important data to some other storage solution outside of the CECI clusters. Here I'm showing some information that you can find on the Wikipedia entry for BGFS, just to show which kind of performance you can get. But in the case that you are able, you have a special kind of job, a big MPI job running in multiple nodes, but doing also parallel I/O. In this case, if you for here, they are showing a different what you can get for this kind of parallel file system if I stack more and more servers, providing these which are set up to work as a whole as a BGFS file system. So in this case, on a single server of this storage cluster, is able to provide, if I do I/O on the local disk of a single server, I get about 1 gigabyte per second, so like the order of magnitude that we get on a single workstation. But yeah, if I stack a bunch of this server and I set up them to provide a BGFS file system, and if I run a special job that is able to profit of this and with parallel I/O, you see that they are able to get a throughput of up to 20 gigabytes per second. But well, here you can have some links for the one who are curious to see how this kind of solution works. But remember, it's not just magically I stack servers and I will increase the bandwidth. I have to do a lot of work on my code also to be able to do the parallel I/O. So in the case of Hercules, well, if you see in the details of the CECI website, it is meant to be used only for single node jobs, not for jobs distributed among different compute nodes. So by how the cluster is set up, you will be able only to run jobs using cores up to the amount of maximum cores that you have on a single node. And the Hercules, it doesn't have it does have a server providing a global Scratch area, but it's set up similarly to, it's an NFS service providing this global Scratch area. It's dedicated, it's separated from the one providing the home. But yeah, it's still that's a single app link to the interconnect to provide access to it. But yeah, well, you can of course use it from your jobs, and in this case, it has 400 gigabyte what's called soft quota and 4 terabyte hard quota. So you start writing there, and up to 400 gigabytes you can write freely. But if you go over 400, in between 400 and 4 terabyte, you can write 1 terabyte on a job if you need. But all the amount after you went over 400, you will have a countdown for 7 days, in which you will have to remove your extra data over the 400. If you didn't do it in 7 days, you will be not allowed to write anymore to this area until you clean up and you go again below 400. So the idea is that, yeah, if you have a job that will run in 2 or 3 days, or several jobs, and you know that you are going to dump 2 terabytes, okay, you are free to do it, you can go, but then you must move the data somewhere else. Or after 7 days, you will not be able to write anymore. And here in Hercules, we have different generations of different families of machines. So we have we have the compute nodes going from 65 to 96. They are Intel machines, and in all of them, the local Scratch. So you have available a local Scratch, so local disk on the compute node, and it's based on a RAID 0 of 4 spinning disks. But in the machines from 65 to 96, which are older Intel machines, this RAID is providing 1 terabyte. There's another set of machines, newer AMD machines. So the 99 up to 126. In this, you have 4 terabytes provided also by a RAID 0 of spinning disks. And then you have 2 special nodes, which are which are the high memory nodes on Hercules. Each of these 2, so the node 127 and 28, they have 2 terabytes of RAM, and you will be able to use them only if your job, if you are running a job, a Slurm job, that you learn that you must request the amount of RAM that you are going to use. If the total amount of RAM is more than 500 gigabytes, then your job will be scheduled to run on these nodes. But so you remember, if you are running a job that will that can possibly that will run on the high memory node, the local Scratch is bigger than the rest. It is up to 8 terabytes. The same as Lemaitre 3 and NIC5. This local Scratch folder is deleted after the job is finished. So you must remember in the sequence of commands of your script to copy over this data somewhere else. You can use the global Scratch for that or the whole. And then, yeah, for the case of features, so the the Intel machines and the AMD machines, they can you can point, if you want for some reason to point specifically to them, you can add a keyword in the, you can add an option in the Slurm script, the -- feature equal Intel or equal AMD, and you will be sure that you land on one or the other. But you can remember that yeah, at least you have always 1 terabyte in this local scratch folder. Remember that, yeah, these compute nodes are, yeah, they have up to, I think, 32 cores. I will check. Yeah, you have 16 cores in the old Intel ones and 32 cores in the AMD. So if you're running jobs less than 32 cores, the AMD, for instance, potentially you will be sharing the node with jobs from some other user. So you have some, if you know that you're going to, for sure that you're going to write up to 4 terabytes, then you might have to add options to reserve the node for you to avoid that your job fails because of the local scratch folder becoming full because other user is also using it. Okay, so focus. So then we have Dragon 2 at the University of Mons. In this case, you have the so in each of the nodes you have a local disk. In this case, is RAID 0 of 3 spinning disks, providing 3 terabytes for this local scratch partition. And the only difference, with respect to all the previous cluster is that in this case, the data is not automatically deleted when the job is done. But in any case, it's the script I will show as example. They all consider that the data is going to be yeah, let's say not accessible anymore after the job is done. So it's I will finish the script by removing the local scratch folder. So you must keep the habit of recovering the data somewhere else when your job is done. Because yeah, in any case, it's data that will stay written in a folder inside the local hard disk, so you won't be able to access it easily from the login node. So it's a good habit to have as a workflow in your script. When you write to local scratch, you always recover the final useful data to your home. Or in the case of Dragon 2, it has also a global scratch setup. It's a bit different from how it's set up in NIC 5 and Elementary 3, where you have dedicated, there we have dedicated storage servers deployed as a BGFS, providing a BGFS parallel file system. In this case, it's also BGFS the solution, but the full so all the, let's say, bricks of storage units providing the single global scratch namespace. Those are partitions on each of the compute nodes that you will see transparently from the login node or the compute nodes. You will have your global scratch variable defined with a folder, a path. So you can write their data that you will see from the login node. But yeah, remember, keep in mind that the data is really scattered amount of partition on the different nodes. So in this case, yeah, the total size is smaller than, it's an order of magnitude smaller than the one that you have in the big storage dedicated in the Metro 3 and 5. It's 52 terabyte, but it provides an area where you can write. It's better to especially it can be useful to recover data actually from after you wrote in local scratch, rather to hit in the home to copy it there. But notice that in Dragon 2 the home is quota is smaller actually than the rest of the cluster, so you can make use of this area also. So, yeah. Temporary location for the output of your job until you post-process and you're done and you can move it somewhere else. Again, there are no, in this case, there are no hard quotas, but always please remember to clean up when you're done and you're not going to touch that data anymore, but you need it. So think about copying it somewhere else. In Dragon 1, we have it's an older cluster based in Mons also. In this case, we have so a bigger quota for the home, but we have the local scratch based on a RAID 0 of spinning disks also, providing 1 terabyte of at max. Again, the data is not deleted, but yeah, just keep the habit of recovering the data that you need at the end. And there's no setup providing a global scratch area, but just for portability of the scripts, you will still have this variable defined, but if you check, it's just a variable pointing to the home. So just in case you just want to keep the script using the global scratch variable, it will work here, but it's really pointing to the home folder. So when you in Dragon 1, when you point to global scratch, you're hitting the home. And then so that was discussion of all the so far the let's say local solutions to each cluster. So global scratch and local scratch will be, so you log in on Dragon 2 or NIC 5, you have your global scratch and local scratch from your jobs, but these solutions are local to the cluster. So the global scratch of NIC 5 is the University of Liège next to the NIC 5 cluster, and you have the local scratch is inside the complete nodes of the NIC 5. And the same thing for Hercules and the Metro 3. So each of them has its own solution providing global scratch. So the data you write in global scratch in the Metro 3 is not visible at all from NIC 5 or Dragon 2. But so since almost 5 years already, or 4 years, we you all said any CECI user is free to use any of the CECI clusters. So there was a request of providing some kind of common solution to all the clusters to easily move data from one cluster to another or access. So it was deployed the solution which is known as the CECI common storage, which is an external a storage solution external to all the clusters and accessible by all of them. So in the and you will be able to see it from all the logging nodes and compute nodes from any CECI cluster. And so, as I said, the solution is external to each of the cluster, where the real storage servers are deployed. But you have, in order to access this area, you have on each of the cluster has a server that we call the gateway server. But so it has a server which is physically on the same room as the Hpc cluster, and it's connected with a fast interconnect to the Hpc cluster, and so when you write to the CECI common storage, you are actually writing data to this gateway machine. Then this machine will, from time to time, write to this external storage. But you, from the user side, you will see it actually as any of the other. So you will access it with the environment variable. We will see, and you will see it as a path, like any other storage space. It will be just a path for you. You write there, but keep in mind it's useful to have an idea of what's behind the things, as we will see that provides different performance right into this different location. Keep in mind that when you write there, you write to this machine, and then it takes some time until this machine syncs the data with the remote storage. So actually, if you write there from the method 3, you won't see it instantaneously on mid5. And at the end, this gateway machine is exposing the remote storage via a single network uplink, via an NFS service. As I said, the real servers with their disks, where the data in the common storage is written, they are based in the data center of the University of Liège, and here there's another here at the UCL. And there's a dedicated interconnect among all the universities to actually access these two servers. So this gateway machine is connected to a dedicated connection for this solution. But so especially when you write when you're in Mons, you have the local machine there in the same the local gateway machine, but this machine then from time to time it will write to the servers here at the UCL and Liège. I think the link. There's more. There's a link after for more details in our documentation. So there are four main areas that we created in this common storage. One, all the paths for one, the one that we will point with the CECI home variable from any of the clusters. So the path starting is /CECI/home and then some other folders pointing to your username. So each CECI user gets a folder created in this CECI home area, and you will point to it with the $CECI home. So if I go back here, you see that I have this. So this is a path that I can see the air, you see, and I can stand here. But then all the if I write a file here or any kind of I/O that I do here, and as I said, I'm doing it on this gateway machine, then this gateway machine is copying it to the node server. But I access just transparently as any other. I CD to it, I do CP to inside it or whatever, as the same as any other path. So then we have a special area at CECI, which we call CECI Proj, and inside there we will create folders by request of a PI. If there's a team, a group that needs a common area where all the users of that lab or team want to write data that will share for the different calculations. So by request of a PI, we can create a folder there and give access. We make all the group of persons that the PI request part of the same Unix group. Then that gives you access to all the persons, the users that the PI request. They give us access to a folder where everybody can read and write. Because then, all the other global scratch, local scratch, CECI home, $home, those are all personal areas. So Damian mentioned some approach that you might have if you want to share data with a colleague, but in principle, those are all personal areas. No other CECI users by default is able to read or write in all these areas. So really, CECI Proj is only that thought to be by request, we create there an area for a team. Then we have this area, the CECI transfer area, CECI TRS. And here, in this case, you have the CECI TRS variable, but in this case, there's no echo. It just points to plain CECI TRSF. You will see that here, actually, this is like a big common scratch area. So if you're, it's a good idea that you create a directory here with your username. And then you actually point to then you will point to CECI TRSF and your username. So Lozano in my case. But it's just a big. It's a big area which is thought to be used only temporary. If you have to move a big amount of data from one cluster to another. So instead of, especially thought for the global scratch case. So remember that for the global scratch, especially in the Metro 3 and NIC5, in principle, it's up to 500 terabytes. So imagine that you produce output, you have 10 terabytes that you must move from NIC5 to the Metro 3. So instead of putting 10 terabytes to your computer that you might not have room even, and then downloading them by your internet connection, you can write these 10 terabytes inside CECI TRSF, wait some time, as I said, it will be synced to the remote wait. Just 10 minutes, 10, 15 minutes will be enough. 10 terabytes, maybe not, but well. So wait some time and then you go, you do that from Metro 3, then you log in on NIC5, and when you see that your data is there, you pull it on NIC5 from CECI TRSF. So this area, you see that here we have a quota of 1 terabyte soft, 10 terabyte hard. It works like I mentioned before. So you up to 1 terabyte, you will write. You will be free, but nothing will will be limiting you. But after you go over 1 terabyte, up to 10, you have 7 days to clean up. If you don't clean up, you will be locked from writing any more data there. So the idea is that I have a big amount of data in one cluster that I want to move to another, so I copy it there, and then I log into the other cluster and I pull it from there. So the path will be the same. This is for the common storage. The path is pointing to this remote storage. The path will be always exactly the same for many of the clusters. So that's the main idea of this. It's a temporary location for moving big amount of data between the clusters. And then there's another, you will see as you do ls/cc, there's another area, the soft area that it's used by us to provide the software that we part of the software that we provide as modules. It is installed there. And as I said, if you want, you can follow from the slide. You can click. You can follow that link, and you will have a very detailed entry in the documentation, more or less explaining what I just said of each of the areas, each of the 4 areas that we have on the common storage. But yeah, there are some more details. And so, yeah, I mentioned, yes, during the presentation, we have these different storage areas. Some of them have quotas, some not. So if you want, the quota is different. So in Dragon 2, the quota, the maximum data that you can store in your home is 40 gigabytes. On the Metro 3 is 100 gigabytes. But then, yeah, you will start using here, you will start writing data on each of these different locations. So we provide a command that will clearly print a summary of all your space, disk space being used. So if you run it from Dragon 2, you get the information on how much you use, the limit, and also the amount of files. I didn't mention it before, but there are sometimes limits enforced not only on the amount of data, of blocks being used, but also on the amount of files. Because that also, each file system has not only a limit on data that can be stored on it, but also a limit on the amount of files that can be stored. So in some cases, we'll check if this. So in here in NIC5, which is in NIC5 we have a limit for everything, but for the 2 local storage areas to the cluster, so home and global scratch, we have a limit for the amount of data and the amount of files. For CECI, the CECI home area, we have a limit for both also. For the transfer area, in principle, we don't enforce, as I said, we have the 1 tera soft, we can go a bit higher during 1 week. But we don't have, in principle, a limit enforced for the amount of files. But so then, of course, if see if I log in on the Metro 3, and if I print the CECI, my quota here, then of course, as I say, the CECI home and CECI transfer, they are coming from the remote storage. So the information that I get must be the same from any of the clusters because it's the same single remote storage. But then, yeah, we have, well, in this case, global scratch is it's just printed there as /scratch, which is the starting path of the global scratch area. But yeah, so this is the global scratch of Lemaitre 3. But as I say, the global scratch and the home are local for each cluster and independent between them. So remember, this command is super useful because yeah, as you will start using the cluster, you will write to all these different locations, and yeah, it's hard to keep a picture on how much data you have at each place. And then, yeah, how, but before, so this is the last part showing an example of jobs. So do you have some questions so far? Or see in the chat? So then, yeah, we will see. Yeah, just yeah, an example of the thing I was mentioning in your script, your Scrum script. How would you put the commands for copying your input to one of these places, running your job, and pulling it. So we have, I mentioned already, I showed you, yeah, when I was switching to the terminal, I showed live, that we have these predefined environment variables, which point, so all these are personal to each user. You have these areas where you can just write CD $global scratch and you land there, or you can CP a file $global scratch / a folder, and you copy that file inside this area. So you can do it interactively or in a command in a Slurm batch script. And then, yeah, we have, for the case of submitting a job, then we have a couple of environment variables that are created and visible from inside the job environment. There's the $Slurm job ID, which will contain the value of the job ID. And then there's also the Slurm submit dir, which will contain the value from the folder that you did. So when to submit a job, you must do a batch and the job and the Slurm script. Then your job will be submitted to the queue, and at some point it will start running. But inside this job, so inside the batch script, you can use this variable that will point to the folder where you run the command batch job 1sh. So that's how we access. And yeah, here, yeah, before the, yeah, sorry, the example itself, I show a job I ran that you should not run. I'm just dumping a big file. So the same command I ran, I showed the example at the beginning of doing a sequential write of a 2 GB file. So it's a job in which, well, I'm printing some just information of the host name and the cluster where it will run and the node. And then I write a file in global scratch, in local scratch, in home, and in CECI home. So I do the same command of a sequential DD of a 2 GB file. But you see that here, in the case of DD, I can point, so it will be a big file full of zeros, but I can give to this code or a DD command, I can provide in the of equal the path where I want to write the output. So I just provide the variable, so this variable will be resolved to its value, and that way, with this command like that, you can you can be writing on global Scratch or on home or on CECI home. And the thing is that, yeah, if we run this thing and we do the output, for instance, from elementary 3, we will see that the dumping, so the sequential 2 GB write on global Scratch, we got about 1 GB per second. On local Scratch, where we are using the local SSD on the node, we get about 1 GB per second. So here we are going over the network anyway. We got the same order of magnitude right in there, but if instead we write on, we dump the file on home, we are getting 400 megabytes, so roughly half the bandwidth from local Scratch or global Scratch. And if we dump it to CECI home, in this case, we are getting also over 100 of magnitude. 100 megabytes per second. So yeah, see that in these solutions are an order of magnitude below. So actually, yeah, if your job is doing, your code is doing a lot of I/O at some point, you will be running half. Even less than half as fast during that part as when you're running on the, if you are dumping the data to local Scratch or global Scratch. So if you have a part of your job that lasts 20 minutes doing I/O here, it will take 40 minutes if you do or more. You do it on the other. So it's important, yeah, to get used to using properly this either local or global Scratch or for the I/O of your job. Yeah, so for the case of Hercules, running the same example, we get, well, yeah, here for local Scratch, we were having here a rate 0 of spinning disks. We get about almost 2 gigabytes per second for this sequential write. And then for the case of home and global Scratch, we are also an order of magnitude below. But remember, in the case of Hercules, a global Scratch is also just a single NFS export, like the home. And here, in the case of Dragon 2, also, yeah, we get we had a rate 0 also spinning disk, and we get well of the order of 2 gigabytes per second of I/O of this sequential write on local Scratch, and then well, we are at least on the same order of magnitude for global, but below for home and CECI home. So for the job submission, I think Damian mentioned this on his presentation. In the CECI website, you have this in the quick links, the job submission wizard, in which it will help you actually. Well, here you have many different options to detail for your job, the kind of job, the amount of cores that you would use, if you are going to use GPU or not. But you have also a section to define that will help you to prepare your job for using different file systems available. So you can choose here local Scratch or global Scratch, and it will propose you some approach for how to use in these areas from your job. So as you see, yeah, here in the case, if you choose to use local Scratch for your job, so it will be a job that will run inside a single node. You see that here it will propose you to do some the creation of a directory inside local Scratch. So this is the job that you are, the script that you are going to submit to the queue. And so you have the header asking for the resources for your job. And then you have here, yeah, the creation of a given directory inside local Scratch. and then you will copy inside this folder your useful input, but your required input. You will, well, here in the middle, you will have the execution of your code, and then at the end, yeah, before finishing, as I mentioned, you will have to copy from this folder you created, and where you copied the input inside local scratch, you will copy it over recoding here using the slurm submit dir variable. So yeah, for the well, in any case, you can see it then clearly yourself in the go yourself on your own to the website. Here you don't have it's not clearly seen, but you can go to the website following the link I mentioned and check. And so in any case, I'm going to show a small example, read interactively, that I copied already in this inside this in this folder that you all have access. So it's inside it's on the common storage, it's a approach, but yeah, this folder has permission for any user to read. So if I yeah, you see that there you have so you have two .sh files, which will be the job scripts, and you have two small Python codes. My code 1.py, my code 2.py, and an input file. So it's a very simple example just to illustrate so just I will show you first what this very basic code does. So here those files that those Python files that are on that common folder, I just copied it to some local folder inside my home, and then I showed the input. It just contains a number, an integer, 1000, and then my code 1.py. It will just read the value on this input file. It will, so I import NumPy, and then it will create an array up to the value that I read from the input file. So in this case, the input file has 1000, so it will create an array from 0 up to 1000. Yeah, I put the lim +1, otherwise it will be 999. And then it will just, so it initialize an array of 0 to up to the limit read from that file. And then I just write a text file with each value of the array. So if I, well, you already saw that we need to load modules to have a fine. So in order to have a Python with NumPy and SciPy, we have this path. We load this, and then we have a yeah. Then we We have a Python environment that has NumPy available. So we will be able to run this code. So if I run the thing, it will read the input in up to 1,000, and it will write. If you saw, it will write in long.out each value of the array. So this is just a text file with 0 up to 1,000. Then we have this my code2.py, and this thing will read this long.out. It will store them in a NumPy array also, defined by all the values from this long.out file. And then it will use add the reduce function or method from NumPy to add up all the values of the array. So this will basically, in this case that I printed from 0 to 1,000, it will add up all the numbers from 0 up to 1,000. And then it will write, so it will provide me the answers in this, we return the value in this res variable, and then I write result.out with this value. So this should do this, and this should, and in this should produce result without that contains the value of adding up all the numbers of the array. So that's so this example having two different codes being run is just to illustrate how you would then imagine that you want to run this code, and you would run this code. Imagine a more complex code that you can run it with different input files, different values producing different results. So then you, for instance, create a folder, run 1,000, because with that you tag. So I have my folder run with 1,000. So this is just one particular case of input in being having the 1,000 value. And then, we submit this, the first. So we will submit the first show, and I'm checking if it's visible. So we will, in the header, we will request the resources that we want. In this case, we asked just for a single core and 15 minutes. I asked for 2 GB of RAM. Way less would be enough for sure for an array of 1,000 integers. And then we do the module load of what we require. In this case, we are going to run a Python code using NumPy. So we must load a Python module and a SciPy bundle module that provides me a Python environment with this. If you just log in the cluster, you write Python enter, you will be on a very basic Python 2 environment. So for that reason, I was mentioning in the beginning, we must, if you are not still, take your time to get used to how to use the software we provide as modules. So we have the module load section to get the software I want to use. And then here it's a little bit different than the proposition in the wizard. Here I define a variable called rundir, because it will be the running directory of my job. equal to local scratch, and then I just add slash room show ID to have. So run there, I know that it will be unique that way because it will contain for sure, yeah, this value that it will be each Slurm job gets a unique job ID number. So I know that this path will be unique. Then I create this run directory. We do a CP from. So here in the folder I'm standing. I have named this input underscore 1000 just because I want to tag the case for which I'm having the input. So in a more complex code, you might have a more complex input file with many different parameters, but you will have your own way to tag. So this is the input case, whatever. But the code then expects the file input.in to be in the directory where it will run. So see that I'm copying it by my particular case, but naming it input in on the destination in the run div. I CD there. So then, yeah, when this will start running in the compute node, I'm creating this on the local scratch partition local to the node, and I'm doing a CD there, and then I execute my Python code after being standing there on the local scratch directory. And for instance, you see that you can have your binary, or in this case it's just a Python script. So you can have your code or the binaries if it's a compiled code somewhere else. For instance, you can have it on your CECI home folder, and you can execute it. You are standing on the local scratch, but you run a code which is located on the CECI home. But yeah, as you are standing on run div, you will do all your I/O from that running directory, and then we will at the end. So this is the first code that reads the value and input and creates the long.out with the array written to this long.out file. And I see that after I run this, I recover the long.out and I copy it to the Slurm submit dir, which remember this will be the value of the directory where I executed sbatch my job.sh. And at the end, as I said, right, we run this in Nick5 where this is anyway run by the Slurm configuration on this will be run in any case, but as in Dragon 2 is not run, then it's a good habit to have it always. And remember that local scratches exist only during, so everything I copy there and everything that I produce inside there, I must recover it because it will be gone when the job is done. So yeah. For that reason, I'm recovering it to this room, submit directory. So I will show you that that I have my. You see that I have my code here located in the. Well, there's some small stuff, but here in CECI home bin. I have my code 1 and my code 2.py. I don't need it to, I will clean the screen. You see here, I don't need to have the binaries of my Python code. It can be somewhere else. Here, I will remove this from the test. So here, I should have the, we start like this. We have just the file I named input 1000, and the code is on the CECI home, but my script has the information from where to find the binary or the script my code. And yeah, then SQ minus U, my username should have here. Yeah. So the job was submitted. It got this job ID, and now it's running on the node 001. I put while the job is running. If I fast enough, yeah. You see here, I did an SSH to I was in the login node. Now I'm in the node 001. And here I do have the local scratch variable. Okay, I was, yeah, I think the variable itself, yeah, it's only accessible from the value of the variable is only, yeah, I was kicked because my job finished, but the variable is actually only defined inside the job, the environment of the job. But if I knew it, I could have do an ls. But so what happened is that what we detailed, the job created this folder inside local scratch on the node. It produced the long dot out there, and then at the end, you see that I have at the end we had this to copy from the running directory back to the slurm submit dir. So slurm submit dir is this path, the one from where I run this batch. So I got the long, well, won't bring the full. I got the long.out file copied back to the submit directory, the one where I run this batch. So I got this, and then, yeah, imagine that, yeah, you have a job that you run something that produces an output, but then you must post-process that. So in this case, the post-processing of will be like reading it's the mycode.to, which will read long.out, and it will add up all the values, and it will print the result in result.out. So now I run this second job, which will create also a run directory, copy the long.out to the run directory, run the mycode.to, and then bring result.out to my submit dir. I will see if now. I have an alias defined in the SQ. Yeah. So it's running in Nikfy 001. And I think, yeah, but this is the global scratch. I forgot how they. Attempts. So the local scratch starts like this. Yeah, you see, this is the. Yeah, actually, it has twice. So this is the folder where it was copied. So I am on the. Wait, I will clean up. So I am on the node where my job is running, and yeah, for the job, the local scratch on Nikfy is actually always by default is created inside the job. Yeah, I was kicked, but it's created starting with that path. So TMP scratch, then the username, and then the job ID. I have an extra job ID because we created local scratch slash Slurm job ID. But you see, yeah, that my file was copied there, the long dot out for this. And then at the end, it was written there, the result dot out, but I told at the end of the job local scratch 2 to do a CP of result dot out to $slarm submit deal to get it back to the submission directory, the one where I run dispatch. And here I have the result dot out as expected. So you see how, yeah, the code is super simple, but it's just to give you an idea of how would you organize your workflow for writing inside local scratch working. Yeah, so if you have a, so in this case, I artificially for if we see CECI home being my code, well, 1 or 2. I artificially added and sleep 60 to make it run for 1 minute because yeah, these two things are immediate, like adding 0 to 1000 and writing the file. So that gave me the time to do the login and see what was going on there. But then if you have a job that it's going, yeah, you will have, of course, job that will run for hours or maybe days. But if you want to check what's going on with your job, then you can, while your job is running, you're allowed to SSH the node and check inside the local scratch folder of the node what's going on, what's being written. In case you don't have enough information here, you see that for each submitted job you get by default. So for the first, the job ID was this number. You get by default what your job would print on the screen if you run it interactively in the terminal. It's written in the in this file, slurm hyphen the job ID.out. So if your job provides useful information on the screen to know the status of it and which part is it, you can just check on your submission directory. You can check the .out. This is what your job. If I show again the local test, if I just run Python my code2.py interactively, you see it's what would print on the screen if I run it interactively. So in principle, that's yeah, that was all with this presentation. I remember again. I put again the warning. So now we went all through the detailed discussion of all the different the global scratch, local scratch at home, the CECI common storage. So remember this. So be free to work to use these areas. You have the quotas. Keep the data there as much as you need. But for critical important data that you produce, copy it over somewhere else. It's still rare that we will have an issue causing data loss, but it did happen already. So it's not usual at all, but unfortunately it did happen. Especially the local scratch and global scratch, I think, especially those think of those as temporary location. Really, but yeah, for $home and $CECI home, we can be a bit more confident. But just think for real, yeah, once you produce important data for your thesis or whatever, just copy it over somewhere else. Yeah, and this is the very last slide. Just so in the Metro 3 and 5, we have the dedicated global scratch based on the parallel file system with their dedicated servers. But actually, in Dragon 2, we do have it. But for in all cases, if your job will run in a single node and the space provided in local scratch is enough, then the most performant area to do I/O is local scratch. It's local disks connected, but accessible from the node itself. So if your job runs inside the node and the space provided by local scratch is enough, then prioritize to use that because that will be the most performant always. But yeah, remember that the space is about, especially the Metro 3 and NIC 5, they don't, as they are meant to use for big and BI jobs. They have a dedicated global scratch, and local scratch it was on the order of just 200, 300 gigabytes. For Hercule, Dragon 2, and Dragon 1, local scratch was 1 terabyte or more. But yeah, it's usual sometimes you will find it the instructions on a website of running a given job, that thinking in running them on a single workstation, that they will tell you for temporary I/O, provide the output to your code to /tmp, but yeah, never do this because in the cases of the cluster we had the dedicated local scratch partition. So if you see a recommendation of /tmp something, just change that for $local scratch / and again, remember to copy the data somewhere else.